The global transition to clean energy relies heavily on infrastructure, like the 15-megawatt direct-drive offshore wind turbine. Direct-drive architectures eliminate high-maintenance mechanical gearboxes by connecting the massive aerodynamic rotor straight to a specialized generator. Parallel to this civilian deployment, modern naval defense relies on operating within the extreme, unforgiving confines of a nuclear submarine's pressure hull, where every cubic centimeter of displacement is fiercely contested by life support and weaponry. Meanwhile, the aerospace sector is aggressively transitioning to highly electrified architectures. Platforms like the fifth-generation F-35 fighter jet require high-power actuators and generators engineered to fit within incredibly narrow, stealth-optimized aerodynamic profiles. If aerospace or naval engineers attempt to extract the rare earth permanent magnets powering these systems and substitute them with conventional copper and iron alternatives, they incur an impossible 300% weight penalty. That massive influx of dead weight physically prevents an F-35 from achieving its required combat radius, just as it makes an offshore nacelle far too heavy to economically support on a floating marine foundation. Neodymium Iron Boron permanent magnets are not an optional, incremental optimization. They represent a binding physical constraint for modern engineering that cannot be negotiated or engineered around. Strip away the multi-million-dollar airframes and heavy marine steel, and the entire architectural framework of these industries collapses down to a single, highly polished block of metallic alloy. The strategic geopolitical bottleneck constraining clean energy and advanced defense originates entirely from the immutable laws of quantum mechanics. To understand why global superpowers are locked in a supply chain battle over the specific material, we have to track its macroscopic power straight down to the isolated spin of its electrons. We must follow this material from its fragile quantum state through the violent, extreme thermal and mechanical forging required to weaponize it into an industrial magnet. Mastering the atomic architecture of neodymium is the absolute prerequisite for technological and military supremacy in the 21st century. Inside the neodymium iron boron crystal lattice, chemically expressed as Nd2Fe14b, the elements strictly divide their labor. Iron acts as the magnetic engine, while neodymium serves as the structural anchor. The 14 iron atoms packed into the unit cell generate the overwhelming majority of the raw volumetric magnetic flux, utilizing the high energy of their itinerant 3D electrons. But iron is exceptionally vulnerable to ambient thermal energy. Without an anchor, the magnetic domains of the iron lattice easily randomize and flip their orientation under ambient heat, completely canceling out the macroscopic magnetic field. This diagram illustrates the specific quantum architecture mapping the neodymium 4F core to the iron 3D band. The neodymium atom possesses a set of 4F electrons entirely hidden behind its outer valence shells, shielded from chemical bonding with the surrounding lattice. This isolation preserves unquenched orbital angular momentum, meaning the electron's rotational energy is not suppressed by its chemical environment. The surrounding atomic lattice generates a crystal electric field, an intense electrostatic force that forces neodymium's oblate, disk-like electron cloud to align strictly along a single vertical axis. To bridge the gap, the neodymium atom uses its outer 5D shell. This shell couples the massive, chaotic magnetic flux of the iron band directly to the rigidly locked orientation of the isolated neodymium core. This quantum synergy generates extreme magnetocrystalline anisotropy. It physically locks the material's magnetic domains into one unbreakable directional axis. Translating this subatomic anisotropy into a functional macroscopic block requires extreme industrial manipulation. Simply melting the raw metals and casting an alloy destroys its power because random crystal growth cancels out the competing magnetic fields. First, the solid master alloy must be destroyed. Manufacturers use a process called hydrogen decrepitation, exposing the metal to hydrogen gas to severely embrittle the solid structure until it physically shatters. High-pressure inert gas inside a jet mill violently crushes these shards into a fine powder, reducing them to particles just 3 to 5 micrometers wide. This precise dimension is a strict metallurgical requirement. Every individual microscopic powder particle must be an isolated single crystal, ensuring it contains only one unique directional magnetic axis. This loose, uncompacted powder is carefully deposited into a precisely machined press mold. Before the heavy metal rams apply any physical pressure, massive electromagnets surrounding the cavity flood the loose powder bed with a Tesla-class magnetic field. The external field exerts extreme physical torque on the uncompacted material. Billions of jagged particles physically rotate in three-dimensional space until their primary claxes snap perfectly parallel to the external flux. Macroscopic magnetic power exists solely because industrial presses physically bully billions of microscopic quantum anchors to face the exact same direction before they are frozen in place. The press ejects a highly fragile block of aligned powder, known as a green compact, which immediately enters a strictly controlled vacuum furnace, heated to roughly 1050 degrees Celsius. Standard solid-state heating cannot physically close the empty space between the jagged powder particles to reach the mandatory 99% theoretical density. To survive, the block undergoes liquid phase sintering. Inside the furnace, the primary magnetic grains remain entirely solid. However, a secondary neodymium-rich phase distributed throughout the powder melts into a liquid metallic glue. The extreme capillary pressure of this liquid phase acts like a vacuum, physically pulling the solid grains tightly together to completely eliminate any internal microscopic voids. Yet, even perfectly sintered magnets harbor a critical operational vulnerability. If exposed to the severe operating temperatures inside an offshore wind nacelle or a supersonic jet engine, the heat overcomes the atomic anisotropy and demagnetizes the alloy. This shows traditional sintering versus grain boundary diffusion, a post-sintering process that immunizes the magnet against thermal failure. Manufacturers diffuse heavy rare earths like dysprosium exclusively along microscopic grain boundaries, isolating each neodymium grain inside a protective, heat-resistant shell. Grain boundary diffusion represents peak material efficiency. It strategically locks thermal resistance into the exact microscopic borders where demagnetization begins, entirely avoiding the dilution of the block's core magnetic flux. Scaling back up from these microscopic grain boundaries, the physical realities return to massive platforms like the 15-megawatt direct-drive wind turbine. The quantum spin of the 4F electron, combined with the extreme density achieved through liquid phase sintering, translates directly into torque density. Torque density is a metric defining a motor's ability to generate immense rotational force from a highly confined physical footprint. This chart shows the generator mass breakdown for 15-megawatt offshore turbines. To capture massive kinetic energy without a failure-prone gearbox, a single direct-drive generator demands hundreds of tons of these highly specific permanent magnets. Attempting to replace this architecture with magnet-free electromagnetic alternatives forces the motors to draw massive amounts of electrical power, which rapidly generates a fatal thermal overload for the vehicle or nacelle housing them. Because of this uncompromising physical constraint, the clean energy industry is forced to compete for these exact same elements against equally desperate defense and aerospace programs. This torque density is a law of physics dictated exclusively by the geometry of the neodymium 4F electron orbital. It cannot be bypassed by clever software logic or conventional metallurgy. Because there is no non-rare earth substitute available that obeys these specific physical laws, the global supply chain remains rigidly anchored to the nations possessing the capacity to refine these metals. The global transition to next-generation clean energy and autonomous defense is entirely bound by our capacity to manufacture and secure the subatomic power of neodymium.